Hello everyone, I hope everyone is doing great. So I am Radha Kumari Pani, Assistant Professor at Vedang Institute of Technology. So in last classes, we have discussed about the small regarding interfaces. So let's start with today's topic, that is boundaries in single phase solid. So this will be the last topic in interfaces in material chapter. Okay. So, what is boundaries? Generally, we can say boundary means it is the interfaces between two solids. Generally, we are considering here a single phase polycrystalline solid, okay, solid-solid interface. So, boundaries are created due to the misorientation of the crystal, or we can say grains that present in the polycrystalline solids. So the boundary is known as grain boundary, and here the important thing, we are considering the two solid of the same phase, or we can say the homophase. Okay, so the different types of boundaries are created due to the different types of misorientation of the grains in the polycrystalline solids. So basically we are going to discuss about two main types of boundary, that is, one is tilt boundary and another one is twist boundary. So from the name we can say, or we can correlate what is tilt boundary and what is twist boundary. Generally, the tilt boundary is created when the two solids, okay, when the two grains are come together in the same plane, or the two grains are parallel to each other, or we can say the axis of rotation. Here we can say this is the axis of rotation is parallel to the boundary plane. This is known as the boundary plane, and this is known as the rotational axis or axis of rotation. Okay, when the axis of rotation is parallel to the boundary plane, that boundary is known as tilt boundary, and when the axis of rotation is perpendicular to the boundary plane. So these two grains are situated is like this in the twist form. Okay, this is in tilt form, one solid in this type and another solid will be in small tilt. Okay, but in this case the twist form, so that the boundary, this is the boundary plane is created, will be, and the axis of rotation will be perpendicular. Suppose this is the boundary plane and this is the axis of rotation will be perpendicular to each other. So that type of boundary we can say twist boundary. So here then again the two types of boundary, one is low angle, what is low angle boundary, and another one is what is high angle boundary. Generally the misorientation angle, when the misorientation angle is less than 10 to 15 degree, that is known as low angle boundary, and when the misorientation angle is greater than 10 to 15 degree, that boundary is known as high angle boundaries. So here low angle tilt boundary, we can say the lattice, this is called the spacing. Okay, the spacing between them is same as B, we can say this spacing is same. Okay, and here is known as the misorientation angle, the misorientation angle here theta. Okay, so we can see that the low angle tilt boundary is an array of parallel edge dislocation. We can say we can see here the boundaries is here. Okay, and the it is so of like the array of parallel edge dislocation. But in case of twist boundary, we can see this is like screw dislocation. This is known as the cross edge of screw dislocation. And when one important thing we can say, so here the small angle, so we can say the lattice point or the atoms can perfectly fit together to the boundaries. Okay, due to the small free volume and due to the small distortion, we can fit the any lattice point. But in case of high angle boundary, we cannot fit. Here we can see here these are the open disorder structure, so we cannot fit the small lattice point because of high distortion. Okay, the here in case of twist boundaries, sorry, in case of high angle boundaries, the bonds are broken in high angle distortion, so that the energy will be high, the boundary energy will be high. Okay, so here in the low angle boundary, however, most of the atoms can fit very well into the lattices because there is very little free volume. But in case of high angle boundary, we cannot fit, the poor fit. Okay, because there will be high open disorder structure. So corresponding to the grain boundary energy, if you are plotting the grain boundary energy in y-axis and the misorientation angle in x-axis, we can see there will be sharp increase in the grain boundary energy. Here, this point is, let the misorientation angle is 10 to 15 degree in this, but below that low angle boundary and above 10 to 15 degree high angle boundary. In case of high angle boundary, the grain boundary energy will be high. Why? Because the breaking of bond will be in high disorder state, so that considering to that the grain boundary energy also will be high. So here there is one specially high angle grain boundary, special type of boundary is there, where the high angle grain boundary means it will be, the misorientation angle will be 10 to 15 degree, but the energy, okay, the orientation is like that, the energy will be less from that of high angle boundaries. Here we can see one example, that is FCC in face centered cubic metal 111. This is the Miller indices. In this type of closed pack structure, we can see the specially high angle grain boundaries. Okay, here this will be the open disorder structure, but which have the significantly lower energy. So this is one type of coherent twin boundary. In the next slide, we'll see what is twin boundary and what is coherent twin boundary. See, here the image is shown here. What is the twin boundary and what is the twinning plane? If similar, if the twinning boundary is parallel, okay, lie exactly parallel to the twinning plane, so that the atom can fit perfectly into each grain. Okay, if the twin boundary is not parallel to the twinning plane, that type of boundary is known as incoherent twin boundary. Okay, here we can see same the energy, grain boundary energy with the misorientation. If angle we are plotting this is the minimum energy in case of coherent twin, and this is the high energy in case of incoherent twin. In incoherent twin, there will be no parallel. Okay, here we can see the incoherent boundary means the twinning boundary will be across the plane will be not parallel to the twinning plane. But in case of coherent, there will be parallel relation to each other between the twin boundary and between the twinning plane, so that the energy will be less. Here, structure of interfaces. So it is the like one of the major factors. So we can see the many engineering material. We can say according to structure of interfaces, there will be what changes in the phase transformation, and basing upon that the application will be changed. So structure of interfaces is quite important. Okay, so basically we are considering here the solid interfaces, and there will be also solid liquid and solid vapor interfaces. In the solidification of a single crystal will be of solid vapor interfaces. Okay, so interfaces in the solid interfaces, we are considering what is grain boundary and what is twin boundary. Okay, so now there will be, basing upon the structure of interfaces, there will be mainly three types of interfaces as there. One is coherent interface, another one is incoherent interface, and the third one is semi-coherent interfaces. Okay, first, what is coherent interfaces? Coherent interfaces means it is the one type of interfaces which is parallel, across which there is lattice planar continuous. Okay, in the next slide we will see the diagram. Coherent interface means it is the interface across which the lattice planar continuous. But in case of incoherent interfaces, there will be no continuity across the plane. Okay, so in the semi-coherent, there will be in small there will be two types of interfaces we can see in case of semi-coherent interface. There will be continuity and also there will be discontinuity. Here, from the diagram we can better understood. Okay, here. First, see what is coherent interfaces. Coherent interfaces means the interfaces across which the lattice plane are continuous. Okay, so there will be small distortion, so there will be energy will be small, minimum. And the example is nickel 3 aluminium are precipitated in nickel based superalloy form the coherent interfaces Okay, with the nickel rich matrix. And another example is aluminium lithium and aluminium copper. Okay, so certain twin boundary can be coherent, so known as coherent twin boundaries. So here we can see this is one type of coherent interfaces. See the lattice here the lattice spacing are same, and there will be continuity across the lattice plane, continuity. So this is known as coherent interfaces, and but the composition here is different. This is one same crystal, but composition is different. Okay, so in case of some coherent, there will be strain, there will be without strain also is there. So here we can see the spacing. Here also there will be continuous interfaces. Okay, but there will be without strain, but here it is different crystal structure. Here the crystal structure is same because due to the same lattice spacing, but composition are different. Here the composition is different and the different crystal structure. Here it is the example of coherent without strain. There will be no strain here. Here we can say coherent strain. Here there will be some elastic strain between the lattice spacing. The interfaces is here. There will be different composition of the crystal with same crystal structure, but the interfaces is created that will be coherent strain. The region with tensile stresses. Here, what is semi-coherent interfaces? Semi-coherent means interfaces across the which some planes are continuous and some are not. Here we can see up to this is continuous. Okay, up to this, and this is not discontinued. Again, there will be some continuous, again discontinuous, again continuous, again discontinuous, like this. Okay, this is known as semi-coherent interfaces. And the last one is incoherent interface. Incoherent interfaces mean there will be no continuity of lattice plane. As you can see, the lattice, this is discontinuous. Okay, so this is the example of incoherent interfaces. So generally, based upon the structure of interfaces, there will be three types of interfaces: coherent, incoherent, and semi-coherent. In the coherent interfaces, the interfaces across the lattice plane is continuous, as we can saw. In incoherent interfaces, there will be discontinuity, as you can see here. But in case of semi-coherent, there will be some continuous, and after which there will be some discontinuous. So these are the three types of interfaces. So up to this, your interfaces in materials is completed, the chapter. In the next class, we will start the fresh topic, that is solidification. Okay, then after solidification, we will cover the diffusion transformation and diffusion rest transformation. Then your in the phase transformation of material, that will be finished up. Up to this, today's class. Thank you so much. Have a nice day.